What's going on, everyone? Let's talk about related rates today, okay? And related rates are basically just finding the rate at which one quantity changes relative to another. And so just to kind of warm up our brains to what we're about to talk about, right? Let's take our position functions, right? Position, velocity, and acceleration. We've been working with these up until this point, and we know that if I were to give you a position function, s of t, right? Let's just say I give you this function, position, right, relative to time is equal to, let's just say 3t squared plus 2t. So if I asked you for your position, right, at 2 seconds, all you would do is plug in 2. So you would take the position, right, evaluate it at t is equal to 2 seconds. And wherever you see t, you would just plug in 2, right? And so now if I were to ask you for the velocity, right? Velocity is defined as the change in position as a function of time, right? So what's your velocity, or what's your change in position at 2 seconds or at 3 seconds? You would do a similar thing by plugging in your time, but you wouldn't plug it into your position function. You would actually have to first find the derivative of your position, because velocity, in this case with respect to time, right, is going to be the derivative of position. Okay, so the velocity or change in position with respect to time would look like this. Derivative with respect to time, right, of 3t squared plus 2t. We know that we need to distribute our derivative. So the derivative of 3t squared, based on the power rule, is going to be 6t, because 2 times 3 is 6. Leave the base there, subtract 1 from your exponent, right? Plus the derivative of 2t, which is just 2. So from here, we know that this is your velocity, right? Change in position according to time. Now you could say at 2 seconds or at 3 seconds, this would be my rate of change for my position, right? By just plugging in 2 or 3 wherever you see t. To get the change in velocity though, right, as a function of time, which is the acceleration, same thing. The acceleration with respect to time, right, or the change in velocity as time passes, is the derivative with respect to t in this case of velocity. And so that would look like this, the derivative with respect to t of my velocity function. So that would be 6t plus 2, right? Again, we know that we need to distribute, and that's going to be equal to the derivative of 6t, which is just 6 according to the power rule, plus the derivative of 2, which is a constant, and we know that a derivative of a constant is 0. So all we have for acceleration is 6, okay? And so let's take this concept, and we're going to use this concept of rate of change in a word problem, okay? And so don't be put off, right? This is a word problem. And so today we are going to talk about related rates, but we are also going to learn how to approach word problems or longer problem prompts, okay? First thing you want to do is you don't just want to go in here and start looking at numbers. You want to read through it and find the important parts. So number one, right, what are we trying to find, right? And then two, what are we given, okay? So separate your word problem into what you're given and what you're trying to find, and that will simplify your process a lot more. So let's read through this, okay? This represents a water trough and is being filled with water. So this dash here represents the top layer of the water. So all this is water in here as well. The width is 1/3 the overall depth of the trough. So let's just write that. The width, right, is 1/3, or let me write that in words, and then we will consider variables a little bit later. So the width is going to be considered 1/3 the depth, right? Find the rate of change. So find the rate of change, keywords here, of the volume of water, okay? Of the volume of water. So this tells you that you're trying to find the rate of change, right? Change in volume with respect to time. This is the term of interest right here. So identifying that is very important, okay? So they want you to find dV over dt when the height of the water is 3 feet. The height of this water, right, is 3 feet. So h is equal to 3 and is increasing at a rate of 2 feet per second. So the rate increasing at a rate of, this is a rate of change, right, is how you should be interpreting it, of your height, okay, with respect to time. And it's okay if you don't see that immediately, but work on recognizing this stuff. So what this is telling you is your change in height with respect to time, right? When they want you to evaluate this, is going to be 2 feet per second. We'll just leave the units out of it just to keep it simple, okay? And also for a 10-foot long trough, a 10-foot long trough. So they're also giving you L is equal to 10, okay? And so based on this information that you've been given, okay, let's see what we can do. Let's dive in now, okay? So you can calculate the volume, right, of this water. So this is, looks like a perfect triangle, right? So a perfect triangle is half of a square, right? We know that from geometry. And so we can say that the volume of water in this column, right, is going to be equal to 1/2 length times width. In this case, 1/2 x, right, times y. If we consider this, right, and to end up being a perfect square, the water just takes up half of that square. So 1/2 base times height, right? But then we have to multiply that by the length of it to get this face and then extend out the volume of our water, so times L, okay? And now we were told that the width, right, the width is 1/3 the overall depth of the trough, okay? And we kind of wrote this here. What this means is that the width of your water, right, of your, just the, not the entire thing, right, not the trough, just the water. So your, I'm gonna write this down here. The width is gonna be 1/3 the overall depth of the water. Sorry about that. In this case, the depth of the water is h, right? So x is equal to 1/3 h, all right? And so we're gonna take this and we're gonna substitute this in for x. I'm gonna do it over the top so that it doesn't interrupt our work in a minute. We're gonna put that here. So this becomes 1/2 1/3 h times L. So let's simplify this out, right? 1/6 times L times h squared is your volume. All right, the left side has not changed this entire time. And so if you think about this, right, this is what we have in terms of the volume of the water, okay? The height here, right, or the depth of the water, we're told that the water is currently filling, right, at some rate. So we know that the height of the water column is going to change. It's going to increase as time continues. And so in this case, the height of the water depends on the time as a function of time. And so the same way that we use in implicit differentiation, right? So recall that in implicit differentiation, right, we said that y was a function of x, right? And so when you took the derivative of y, to x, you simplified this first by doing the derivative with respect to y of your y term, right, times dy over dx, right? This cancels, and then you get dy over dx, okay? Same thing here. So let me take this out. We're going to think of it the same way, except for like this. If we're trying to find the change in the height of this water column, right, with respect to time, we're going to be able to simplify this by taking the derivative with respect to h, right, of our h term, of some h term, multiplied by change in height over change in time, right? Because you cancel this, you get dh over dt, okay? And so let's use implicit differentiation here, all right? So we're going to use, I'll write it right here, implicit differentiation, okay? Differentiation. And so just like we did in implicit differentiation, we don't need to get it in a form y is equal to f of x, right? Or a similar format with different letters. We can just take this thing straight on. So we'll take the derivative with respect to time, right, of the left-hand side. So this becomes dv over dt is equal to is equal to d over dt of, let me see here. Sorry about that. Okay. Yes, d over dt of this entire side. I didn't want to get too ahead of myself. Okay. In this case, once you have it in this form, you're going to hopefully recognize that every term in here does not actually need to be in here, because 1/6 is just a number, it's a constant, right? L represents the length of your trough, which was given at 10 feet. So that's a constant, that's just 10. So you can take both your constants and move them out in front, okay? So at this point, you have dv over dt is equal to L over 6 multiplied by the derivative with respect to time of h squared, okay? And so we said that h, right, is a function of time because the height of this water column will change. It will increase as time goes. And so let's continue this up here, okay? I'm going to rewrite that line. dv over dt is equal to L over 6 times the derivative with respect to time of h squared. We said that, right, h is a function of time, so we have to use the chain rule, okay? And so we're going to use this definition down here, right? We're going to split up our dH dt as follows. dV over dt, that stays the same, is equal to your constants, L over 6. Okay? Here is the chain rule where we're going to do, right, the derivative of the entire thing, right, in terms of h, multiplied by the derivative of just the inside. Okay? And so L over 6 multiplied by, in this case, it's going to be d over dH, right, of your h term, h squared, multiplied by dH dt, because h is a function of t. Okay? And let's move this down. Okay. And so let's simplify what we have, and I'm going to, oh, I'm not trying to move that, I'm trying to move this. I'll move I, I'm just going to delete. Okay. So let's continue, right? Is equal to L at this point over 6 times this derivative with respect to h using the power rule. 2 times 1, 2. Keep your base there. Subtract 1 from your exponent. 2 minus 1 is 1. H to the 1 is the same thing as h. So leave that. Multiplied by dH over dt, right? Change in height with respect to time. Now, remember what our problem prompt wanted us to find. It wants us to find this term, so it's in perfect position. So all we have to do is fill out this right-hand side. L was the length of our trough given at 10 feet, right? It wanted you to find dV over dt, where the height of the water was 3, where h was equal to 3. So plug in 3 for h, right? And when the height was increasing at a rate of 2 feet per second. Change in height over time is 2 feet per second. And so all we need to do is solve this out, okay? So 10 over 6 times 6 times 2, right? The 6's cancel out because this is the numerator, denominator. 10 times 2 is 20. So your change in volume over time is 20. Okay, I'm going to leave out units for now just so you can see what you're doing, okay? So to go over a quick summary of this, right? We said when we are confronted with a word problem, and I didn't mean to draw that line. If we're given a word problem, you don't want to just start plugging in numbers everywhere. You want to look at it and extract the information you're given and what you're trying to find. Once you have these pieces of information, then you can start to fill in the roadmap of how you get from what you're given to what you're trying to find, okay? And in this case, the width was given at 1/3 the overall depth, right? And so we concluded that when you're talking about width, not the width of the trough, but we were concerned with the width of the water column, right? Because we are doing this calculation to see the rate of change of the volume of the water, not the column itself. So x, right, ended up being the width was 1/3 the depth. The depth here was the same thing as the height of the water column, okay? Because as you add water to this column, the height's going to get larger, meaning the depth is going to get larger. We were given the rate of change of the volume, right, as what we were trying to find. And so that's how we determine dV over dt. was our quantity we're trying to solve for. And then they wanted you to find dB over dt when the height of the water was 3 feet, h is equal to 3, and when the height was increasing at a rate of 2 feet per second. Change in height over time was equal to 2 feet per second. We didn't put the units because we just want to keep it clean, right? And the length of the trough was given as 10 feet, right? And then so we calculated our volume based on the properties of a triangle and a square, right? So this was a triangle, and we said that you could calculate this front face, right, the area of this front face, by 1/2 the base times the height. And then to account for the rest of the water column, you just multiply it by the length of the trough. And that's how we got this initial volume equation. We rewrote x in terms of the height because we were given previously x was equal to 1/3 the height. So we plugged this in to here, and that's how we got this term. Okay, the rest of it was the same. We just brought it down. Okay, we were given this, basically the starting equation to work, the starting volume equation. From here, we used implicit differentiation, considering that h is a function of time, because over time, more water is added to the column, and the height, or h, is going to increase. Okay, and so because of that, we knew that we could break up, right, change in height over time. We split that up into d over dh, right, the derivative with respect to h of the h term. In this case, the h term that we had was h squared, right, multiplied by the change in height over time. Okay, and this is valid because if you do this, cancel the dh's, you get dh, right, change in your h term over dt, dh over dt. All right, once we did that, we solved it with implicit differentiation, right? And then we were able to plug in the information that we were given. We were given the height, right, 3 feet. We were given the change in height with time, 2 feet per second, the length, which is 10 feet, and we were able to solve for the change in volume over the change in time. Okay, so I hope this made sense. If it does, good job. If it doesn't, totally fine, right? It's a more involved process. So go ahead and look back at parts if you didn't understand something, or drop a comment or questions below, and I will get back to you as soon as possible, okay? So this was related rates.